Okay, we will continue the optimization for today. So I will give you more explanations and also another examples. And lately, I'm not sure what's happening to the device. I think it's because if not recording, like if I'm just writing in the device and the app, it's working fine. But when I'm recording, it has something trouble with the memory. Although the memory, it's fine. So I hope you don't mind. And I'm suggesting coming to the class to learn it first-hand experience. Okay? Because sometimes the recording might not work and might not. So sometimes if there's trouble, the recording will cancel. So yeah. Okay. Anyway, let me just go through a little bit review for what we have done in the last class. So we'll deal with the problem. Any case that you can make something of it. Probably the example that relate with your daily life includes on if you deal with some sort of selling some stuff, like maybe you operate or maybe you are a vendor in an online shop or online platform that I think today or nowadays it's pretty usual for anyone who has who act as a vendor, right? And you want to make some formulation of your profit, and you want to maximize those profits. So anything that relates to how we can make or how can we make profits, maximizing, and we have some sort of course, the role or the roughly we can say that when we deal with the selling and buying, we need to know the original price, right? Like maybe you are having another vendors and you are acting as a third party, and then you need to also selling those, and you need to think on whether you need some logistics when you need to throw that in warehouse, and you need to calculate the money. I think some of you already done something like this. Okay, and when we deal with the maximize and minimize something, some value, either it's profit, it's any formulation that you can have. Okay. What we are doing is we will relate all those maximum minimum problem with the critical point. So critical point is essential things in our optimization. So what we are doing is we need to find this critical point. We know critical point. It's not always at prime equals 0. Because sometimes when it's telling this, it's also critical point. But for most cases, if we made up our formulations, then the f prime equals 0. This will be the key. This will be the key to find the value that we want. Okay. And after we find the f prime, then we know how to at least take action for our problem. Now, to solve that, before we find the f prime, we need to find first the formula, right? We find the formula. And maybe before the formula, we draw first. Sketch any information that were given in the question. And not this question, maybe anything that you can have. You can relate this to any problem that you have, and you want to optimize from those problems. And the second, maybe you can name variables that changing. Okay. Of course, you have like a fixed cost, variable cost, like something like that. You deal with some to find some profits, right? And then find correlations, how you make these formulations. Is there any quadratic? Is there any cube? Is there any related to exponential functions and so on and so forth? You make a models. In this phase, you make a models. But in our understanding for calculus 1, we will restrict some formulations on only for so we will limit the formulation only for I think I can say like a simple problem. For example, geometric. Either it's area, volume, okay, or even some fixed formula. Maybe the formula are given and you just need to optimize from that formula. And maybe having another set of conditions that you need to think. Okay, and also formula may be related to some graphs. The tangent in the tangent graphs, and maybe it's cuts and making some area, and then you need to look for area, finding critical value of that area. Okay, and then after we did all this, finding the f prime 0, and then we find the c. Okay, we find the c, and then we put the c, and we know how much we will get. Okay? Either minimum or maximum, it depends. Okay? And I'm giving you this question, just illustration on the box, and you have some sort of idea on. First, we need to design. We have the material. We have the limit, right? How large the area, and we need to fold the paper, making a box without the top. Okay, and we can sense that we have this formulations, and this is also essential in optimization. So we will have at least two components, okay, in optimization. First is our formula that we are going to optimize. The second is the constraint. Like for example, in this case, our constraint is this surface area that we have the limited materials, okay, that we need to cut. Right? And after some sort of calculation, we find the f prime through some substitutions. So the idea is, usually probably you will have more than one variable. The idea to make this formula, the optimization formula, only one variable. That's the idea, the only idea. And most of the problem, that's the key. Okay? And after we find in one variable, we take derivative. After we take derivative, we then make it equal 0, because that is our critical point. And after we equaling 0, we get x, and that x will be our goal. Okay? So it depends on the question whether it's finding the x or f of x. Well, maybe it's asking which x that has maximum or minimum value, or maybe it's asking directly maximum minimum value. Then you just input x to the functions and you get the result. Okay? Now, based on this, okay, of course, the question is, it's already find the largest. But then probably you will ask, how to find the smallest? So if you read the textbook, or if you read questions on this section, your calculus textbook will ask the right question. So for example, this will ask largest, not smallest. Do you know why?
Because the smallest is only a line.
All right. So if I take, let me just give you an illustration on how this affect your thinking. Okay. So it doesn't need to be like okay, if this happened, then okay, the largest will be getting this, and this. Okay. So let me give you from calculus perspective of what we done here. Let me give you a question. Wire it has length 1 meter, cut into two pieces. Each piece encloses a square. Find largest area enclosed. Okay, so let me give you some context here. The context, we have wire. We are given a wire with 1 meter length that we cut. But it doesn't mention where to cut. It's just cut. Okay? Cut into two pieces. And then we have now two wires, right? Maybe equal or maybe small, large, or large, small, depends on your drawing. But we just assume one and then we cut and then maybe X. Okay? We just assume that. And then we make each of them a square. A square means the length should be the same. If this is X, this is also X. Okay. But let me just draw what we have. Okay, so this will be 0 to 1. Okay, we cut maybe here. Let's say this is X, this is 1 minus X. Okay. Well, we can cut anywhere and it should be the same. Okay, we just illustrate because this is our let's say variable. And actually, this is the one we are looking for. We are looking for X to find that which one is the largest one. Okay. Now, if this two wire, now we have two, so this is 1 or maybe A, this is B. Okay. Now we want to make a square. So let's make a square. Maybe this is a little bit smaller, the right one. And each one is divided by 4 because we need to make it equal, right? So this will be 1 minus X, 4. Okay. Now the area, the total area. So the question is asking is actually the total area. So we need to add these two. Okay. So the area A plus area B, we need to find which one is not which one. How large both of them? How large? Okay. So the formulations, we are just taking area B plus taking area A. That's our formulations for this one. Okay. So again, we have the 1 meter length is our constraint, right? It's our limit, the materials, right? And this one is our optimizations. Okay. Now perhaps, okay, if we are just, okay, maybe take derivative, make it equal 0, and then maybe we can find something. So take derivative. So x squared is become 2x. 2x over 16 is x over 8. And then negative x, negative 2x is also similar, but minus, right? And then probably we will have 2x minus 1 divided by 8. Let's equal this to 0. Let's equal this to 0. And we are getting x equal half, right? Okay. Okay. Derivative is no problem, right? Anyone can follow. Okay. Okay. Now x is equal half from this 2x minus 1 equals 0. So probably this is our x. So if we try to measure pass the a half, okay. So this will be 1 over 8 squared plus 1 over 8 squared also, right? And this will be 2 over 64 or 1 over 32. Okay. If this is your answer in the test, it seems correct, but it's actually not correct. Okay. So if you write that, the largest area is 1 over 32. This is wrong. Why? Because actually, the question given is asking the wrong question. It should be asking the minimum. Okay. Now, let's see from the perspective of calculus. Okay. Perspective of calculus, let's prove on line number. Okay, line number. Let's say we have, because it has from 0 to 1, let's say it starts from 0 to 1 for the wire. Of course, if it's 0, the wire is gone. Okay. So let's just imagine the wire. And then maybe let's put half here. Okay. And it's like testing the line number, see increasing, decreasing. Okay. Let's put half here. And try to imagine what we have here, and that's our derivative, whether it's increasing or decreasing, whether it's positive or negative. We check maybe around here, maybe what you got there. Maybe 0 to 1 over 4. 1 over 4, negative, right? And 1 over 4, yeah. Okay? It's negative, right? If 1 over 4 is negative. So it should be negative, and this will be 2 over 3. 2 over 3 is positive, right? Check 2 over 3 here is 4 over 3 minus 1 is positive, right? It's positive 1 over 3. So what's happened here? Going down, going up. Is it maximum? Is it minimum? Minimum, right? Okay. You get it? But trust me, in your textbook, all the question is right question. So they don't ask this trick question. Okay. But for example, if you want to make sure that this is the one that you're looking for, you can check with the line number whether it's really going a minimum or maximum. Okay? I hope this logic makes sense. Okay? And can we answer whether it's maximum or minimum, or can we find the maximum value? I think if we are not in the real world and we use limit, okay, for example, limit, we can check the limit. So if we check the limit of each of the endpoint here, let's say the limit approaching 1 from the left, and this is limit x approaching 0 from the right of the function. If we check the limit, as x approaching 0, which one is our function? Going here. Oh, here. Our function is this. So we just substitute 0. We'll get at least 1 over 16. If we approach 1, we will get also 1 over 16. And there is no other options, right? So the only way we can approach is through limit, and it's 1 over 16. But but it seems that it's imaginary or it's not really real. Because if you are here, then it's almost zero, nothing, right? If you are here and you don't really cut anything, if you get it, okay? This is 1/16. So the maximum area through limit is 1/16. Okay. But of course, the conclusion is the question is not really clear, or it's not really correct. Okay. So not the answer that is not clear, but the question is not asking the right question. Okay. But for exercise, your textbook they provide right question. So don't worry. Okay, don't worry. Okay. Now, any question beforehand? But still, if you don't really get this calculus part for reasoning why this is wrong question, then still okay. You still can survive calculus as long as you still keep your optimization rules for these 4 steps correct. Okay? As long as you did this, you know how to derive, you can find the critical point, you still can survive these optimizations. Okay, this is just to prove that the question is not asking the right question. It should be asking not largest, but it should be asking smallest. Okay, let me give you more context on what kind of question that might come. So aside from finding the critical point and finding values, sometimes the question is just given you just illustrations on the formula. So there is no fixed number or fixed like you need to calculate this and finding the result. But maybe you need just to find the relations that is connecting to the optimization. Which one is maybe largest, smallest, maybe optimized, which one is not optimized, okay? So let me give you a little bit more context on that. So let me give you another example. Cylindrical can is to be made to hold 1 liter of oil. Find dimensions to minimize the cost of manufacturing.
comes.
So we have 1 liter, okay, at least that the constraint that we have. So cylindrical, let me just draw some illustration for this can. Okay. So at least we need to correlate the height and the radius for the base. So we need to make the cylinder can. Okay? So the idea is we are going to have all this part in metals, right? It doesn't really matter how much that costs, but we need to find the dimension that minimize. So first, look, this is a circle. So we have 2 circles, and we have this surface area here. Okay, if you are maybe not really into memorizing the lot of formulas, at least circle, you know the circles, right? You have 2 circles, so we can write this is 2 circles. Let me just draw circle, circle. Okay, we have 2 circles. Okay, and then the middle part we can cut, and then we can see that it's actually a rectangle, right? It's a rectangle. So we can see it's a rectangle. This is H, right? According to this one. And what is this? This is the circumference of the circle. I hope it's familiar, right? Not really, you need to memorize that. So 2 pi r. And this is r. So we have the area will be, this is 2 pi r squared for both of these 2 circles, plus the rectangle is 2 pi r h. Okay. So we have the optimizations for the functions. And the constraint, we have 1 liter. We need to make this shape, the volume needs to be 1 liter. So we have the volume, okay? And the volume, every 3 dimension, the volume is the base multiplied by the height, right? Okay. So the volume, let me write here, the volume will be the base is pi r squared, and it's multiplied by height. Okay, 1 liter is equal to, what's the equivalent for liter? Yeah. The m cube, right? No. I'm like, not really complicated. Just reviewing what you remember. Okay. Okay, and I think it depends on the question which units they want to use, but I think I will just use the centimeter cube, okay, because I think for radius and height it will be best to look at centimeters rather than this dm. So let me just take this into centimeter cube, so that this pi r squared h, we have the constraint of 1000. So this will be our constraint. This is our optimization. Okay, and the deal here, you have this constraint. What you need to do with the constraint is the same. You need to take either R or H, and then you can substitute to this equation, so that the equation of this optimization is one variable. That's the key for all optimization problems. So I think we can substitute here, and I think I will substitute. Let me just substitute maybe height. Okay. So this will be 1000 divided by r squared. Substitute to area is 2 pi r squared plus 2 pi r, and then 1000 over pi r squared. Okay, let me just solve this. Okay, that's the equations. Okay, we can write this in terms of a function like that. Okay, and of course r should be positive and should be also greater than 0. Okay, then we can differentiate. We find differentiate with r, with respect to r. So 4 pi r. 1 over r is become negative 2000 divided by r squared. And then maybe we can solve this and make it into equaling 0. But before that, maybe we can combine these two. So 4 pi r cubed. Or we can take this 4 out. Okay. If we are going to equaling this to 0, then pi r cubed will be equal to 500. So we can find the critical number for r should be equal to this cube 500 over pi. Okay, and if you want to check whether this is correct or no, the same way we deal with the previous one, we can take this approach from 0 to 1000, but it's more a difficult number, and you need to think on how this number will correlate. You can check this, okay, and check whether it's minimum, and I think it will be minimum. It will be minimum. And when r is equal this, then h will equal to pi and then r. Okay. Or if you solve this actually, if you solve this 500 over pi, this will turns out to be 2r. Yes.
I think in the H it's 1000 pi r squared. Why is it 2 over 2?
Which one?
The H. You write 1000 pi. Oh, I understand now.
Yeah, we input r, r squared, input r. And maybe let me give you more, a little bit different than these two examples. Or maybe any questions first for this one? So it's actually asking the dimensions. So what is R and what is the height? Or this one.
Okay, so
Yes?
so in the exam, so should we have to check again like you are checking right now?
Short answer, no need. No need. I will make sure the question is correct. Okay.
Professor,
Yes?
H equal to, you just solve it?
Yeah.
Solve the
Yeah, long story short. But if you maybe in the exam not really solve into a simple formula, that's okay. Just write as it is. Okay, let me give you, I think, one more example. Find the point on the curve y equal square root of x that is closest to 0.30. Okay, I hope you can easily draw some essential functions. Okay, essential function include the polynomials, okay, like x squared, x cubed, the square root. Okay. Also, another essential is trigonometric, like sine, cosine, tangent, and also the reciprocal, the 1/x, 1/x squared, exponential, log. That's at least that the list for some essential function that you need to visualize easily in your mind, or if not, then you can draw and illustrate graphically, okay? So that at least you know how they behave. So when we are talking in more advanced and details, or maybe in another lecture, you can have some basic in your mind. What's the graph tells you. Okay? Now, if we have this curve asking the closest. So we need to find the point on the curve of this one that is closest to the point 330. Okay? So first thing, draw this curve, and you can just pinpoint in any point on the curve, okay, because that is our goal, right, to find which point. So let's just draw first. Let's say this is maybe too small. Make it a little bit larger, maybe here. Let's say this is 3, 0, the point. And our curve, maybe make it a little bit there. Okay, maybe that's our curve. Okay. Let's say this is our square root of x. Okay. And then the question is asking, we need to find a point. Let's say the point is maybe here. Okay, let's say we take a point. So whenever you find any unknown, anything that you are not sure which variable, try to name that point. Okay. So for example, this is the point we are looking to point, right? So we can name the point here. So let's just name according to the function. So maybe x and square root of x. Okay, the point. Okay. Now it's asking the closest. Closest means it's asking a distance. Okay? It's asking a distance. So it's asking distance from this point through this reference. And how to find the distance? How to find the distance?
Triangle.
Yes, triangle. So in I think you have 2 points. You want to find a distance in the coordinate system. Of course, the better way to approach that using the triangle. So for example, let me just illustrate. So we have this, this. You want to approach the distance from these 2 point A, B. And of course, this is in XY. XY system or Cartesian system. So this have a point. This is also have a point. So we can say that if we take this x1, y1, x2, y2, then this is the delta will be x2 minus x1, right? The delta also y2 minus y1, right? And then using the d squared is equal then we can find the distance, right? Similar with what we have here. The distance, okay, we'll take absolute value of the distance, the square root of x minus 3 squared plus square root x minus 0 or just square root x squared. Okay. Now, to simplify our problem, because we know that the distance should be a positive, okay, should be positive, let's make it into d squared. Okay, make it into d squared. At least to remove the square root to make our problem much more easy to analyze. And maybe take this as maybe s, okay, just to simplify the d squared. And what we are doing now, we have a new model that takes the name s. Okay. And then we take the derivative of this s, okay, and we have 2x minus 3 and then plus 1, and then equaling this results with 0. So we have 2x minus 6 minus 5, or it's equal 5. So x should be around 5 over 2. And y will be square root of 5 over 2. Of course, you can also imagine take some approach for the line number. Or maybe if not, then yeah, you can use the second derivative to check whether it's maximum minimum. Check the second derivative, that it should be 2, which is positive. Positive means concave upwards, right? Concave upwards means, right?
Why do we have to do second derivative?
Now this is just to check whether it's the minimum or not, because we want to check the closest. Okay. So if you don't want to use the interval, you can derive one more time and check the compactity. You can also do that. Here, this is just to remind you that we can also use the second derivative to check the minimum maximum. Okay. Okay. Well, do you want to have a short break or just continue? Huh?
Continue.
Okay, continue. It's okay. Okay. So we will have we will finish early. Okay. Let me. Okay, this will be the last section on chapter 4. It's called the antiderivative. It's some sort of introduction to integral, but not integral yet. Okay, it's not integral yet. So we'll have the definitions. Okay. So a function, let's say f with big capital F. Okay, we usually take the capital S, the antiderivative, is called antiderivative. Antiderivative of f, small f, on some interval, let's say interval I, if the big capital first derivative equal with f of x for all x in the interval. So we in some sense we are trying to look at, so if we take the f of x is x squared, we're kind of getting that the antiderivative is actually 1 over 3 x cubed. Okay, so we look on how we can reverse the derivative. Okay. It's not integral yet, it's not the integration yet, but it's some sense of introduction for integration. Okay. If you have the integral, you need to plus the constant, right? But it's not. We just take some time to see that if we reverse the x squared, we need to have this x cubed, so that when we derive, it will get in the x squared, right? Okay. Okay, now because there will be, of course, if we start from this big capital F, we can connect to the results of derivative easily. We don't really need to think about constant, right? But if we have another functions that state maybe h, that maybe having a constant for some number, it's different functions, right? But if we derive, it was also the same conclusions, right? The same, if we derive the dx, we'll have the same conclusion. So if f is antiderivative of f, then or the most general antiderivative of f is f of x plus c, where c is a constant. Like for example, to take this this capital F and H, okay, in more sense, make sense. If we take this F prime X, let's say, if this is equal, right, and let's say not G, it's H. Let's say this is equal, the derivative is equal to x squared, okay. We will have, if we take the antiderivative, we need to have a constant, okay, to make sure that this is going to be having another constant, okay. Now, to begin with the introduction, okay, if we have a function that is sine x, if we want to make this into the antiderivative, we can think from, if we derive the cos, it will be negative sign, right? So if we derive negative cos, it will be sine. So from here, we kind of getting a sense that our antiderivative of x for sine is negative cos x plus c. Okay. Now we call this this guessing is we call advanced guessing. And sometimes, although it's a guessing, we can take this advanced guessing in a way that later, if you see some techniques in integral, like partial or substitutions or any advanced method for integrations, this advanced guessing sometimes can help you to answer some of the questions. Okay. And some other functions that we can think and write. Maybe let me write in the next page. Some of them are ln x, we have 1 over x, right? So when we have so f of x will be, let me write here. If f of x is 1 over x, then the antiderivative is ln x plus c.
And if you have the tangent inverse, this will turn out to be 1 plus x squared. So if you have a function that is 1 over 1 plus x squared, you will get the antiderivative tangent inverse x plus c. So the key to know more on the antiderivative or later integral is, I think the very foundation is the derivative formula. Okay? So if you know the derivative of some functions, you can reverse back to what it's become. Okay, so that's the idea. Okay, let me giving you some example for if you see. Okay, maybe giving you an example. Okay, maybe find example. Find f if f from x is equal e to the x plus 20 . So they give all information you need. They give you the derivative of the function, and they give you the constant actually when x is equal 0. So if you try to write f from x, you can write this. So you can have a sense that if we want to take this into the antiderivative, we will have, or maybe directly tangent, and plus c. And then with f0, we will have e0 plus so c will be -2, -1, right? So this is 1. So this is -3. So f of x will be e to the x plus 20 tangent inverse x minus 3. Okay. Now, because we deal with the derivative and now antiderivative, okay. So you have a function, you have derivative, you have second derivative, and now you also antiderivative. So if we combine those together, and you need to predict which one is the graph of functions, which one is the derivative, which one is the antiderivative, I hope you still can combine them together. And you still remember when we deal with the chapter 4.3 when we deal with the graph, how to read the graph. Okay, I think that's most of it for today's class. Maybe let me give you more on the Newton's method, because I think the recording is disrupted before. So basically, let me just review. Okay, although it's not really included specifically on the midterm, I hope the connection from the linear equations, linear approximation, and how the Newton's method will work, they are actually the same principle. Okay? First thing, linear approximation is we want to approximate the functions with some number a that is nearby, okay? And we can make it into a tangent. And when we have a curve, and we have the point that is, maybe we have the tangent line here. Okay. When we just zoom in around this area, the curve and its tangent they look the same. They look the same, right? Okay. Now, because of that, we can take the tangent as our approximation. Okay. Okay. So linear approximation, we need to find the functions, right? We need to find the functions that we want to approximate, and we can check some a, and then is that closer? Is that our value or not? Okay. Now Newton's method, different from the difference between Newton's method and linear approximation is Newton's method, we are looking for x. We need to find x. Okay. So Newton's method, in terms of how we find, is actually we have a function and we need to find the root. We need to find this x. Okay. This x is when the function is 0. Right? The y-axis is 0. So what we did is actually we are rewriting the linear approximation. We are rewriting, and then we make this f of x equal 0. F of x equals 0. And then we have this terms, or rather this term, finally this term, okay? And then how we are applying this. So first we have the first initial point. Okay? It can be any number. So you were giving some information, like equations that you want to find. Which, can you find the root? Okay. So take some random number if you want. But actually you can guess, like maybe it is around 1 or 2 or 3 or maybe 1 point something. Check your x0, check the answer, you get x1. Check x2. When you have several trials, so maybe until x4 or 5, maybe you see some consistency. When you see some consistency on your number, then you get what you find. That is probably your approximation to your root. I think that's the Newton's method. And actually, what it looks like in terms of the graph, this is x0. Take the tangent here. This is your x1. Okay. If you can imagine, this is x1. And then take your tangent again. This will be your x2. If you take another x3, this will be x3. And you will get more and more closer to the root. Okay, that's the key. Okay. So linear approximations, Newton's method, and also mean value theorem, they are all takes the same principle with the same linear equations. Actually, they can be developed from the linear equations. Okay, I think that's just some review. So okay, next Tuesday we'll have more practice. Okay. Chapter 3, chapter 4. A little bit chapter 2, but I think I will focus more on chapter 3 and 4 because that is, I think, most difficult for some of you. And if you have any requests for which part that I need to emphasize, like maybe you don't really understand the class, you can also ask maybe you can ask via Moodle or email that I can prepare for Tuesday class. Okay, so we can prepare more, and also, yeah, I think that's it. I think that's it. Okay.